All right, we're going to review a little bit of fluid mechanics, and thank you to all these professors because I'm basically taking a lot of things from them and their textbooks that they so kindly showcased which ones are good and which ones are bad. So we have like six different. Let me think: one, two, three, four, five. At least a lot of fluid mechanics books. I have a bunch of them, and I've divulged which one's good and which one's bad by looking at them and have densed it down a little bit. So this first portion will be derivative based, basically, and mo more about definitions than anything else. The only one I'm lacking in the definition department, you'll see later on. I kind of didn't cover one part of it too much because I feel like we'll do that later, especially since if I were to do some of the classical tension pull later on derivatives, we're going to do that sooner or later, I think. And then obviously that portion of it is in the fluid book, sixth edition, Polka Carnu or something. So I haven't done that because I haven't looked at this textbook yet. So that's why I've done. But I'll go back to it as soon as I'm done with it. Anyway, quantifying a fluid is more easily deformed than a solid. A fluid flows. A fluid has weaker intermolecular forces than a solid. Example: air, water, gasoline, and blah blah blah. Definitions: a fluid is a substance that deforms continuously under shear stress, as you can see over here. You can see over here in the solid. Maybe I should make it into a box. It may be more appropriate, but it deforms to here and it will not go further. While fluid just continuously goes forward and forever and ever. Over here is the more textbook version of these two things. Um, Still not really anything different so far. So we go over here, solid versus fluid. Solid, a force is applied. Point A moves to A prime. The point then stops. Fluid B is a fluid is applied. The point A continuously moves. The fluid flows from A to A prime to A double prime. And that's pretty much. Velocity vector V can be defined by U, V, W, and pressure P are interest to us in fluid mechanics, scopes of fluid mechanics, propulsion, energy conservation, medical field, and a bunch of other stuff, even Hollywood. Has to have dimensional homogeneity, which basically means this is meters, and this combined must be meters, and this combined must be meters. And you may think that this is arbitrary, and why am I even covering this? It's important for Buckingham Pi theorem for you to actually have some analysis of this. It's not just because we don't. I mean, we're showing it to you because we need it later on, and just trust us, I will need it. And it's actually way further on, so it'll probably be there in like a few days. I don't know. Anyway, SI units are here, and these are the SI units. Anyways, to analyze a fluid, we need three things: mass conservation, mass momentum conservation, energy conservation, and the topics are generally split into two areas: fluid statics and then fluid dynamics. A lot of people think this part is more fun. Fluid statics simplifies a lot of stuff. We'll see what that means later on. Um, so over here are the King equations, as I call it, or the Navier-Stokes equation. And if you were to simplify it a little bit, you'll find that this goes away, because if this is called Euler form. And fun fact, Euler came first, and then Stokes. Very not known too much. Anyway, here's our different forms of it. There's a few different forms that I need you guys to like look at. So the integral form is one that always gets you a little bit. But anyways, I will mention that all of this has a plus to it because not this one. This one kind of has a plus, but kind of does at the same time. But these have plus to it to add different factors. Because the momentum is a force, so you can add electromagnetism. You can add some other Fourier something. Over here, you can add the Fourier heat law. You can other chemical reactions to this. It's very variable, so very malleable. Anyway, fluid properties. The property help distinguish different fluids. There is density over here. Density is mass over a unit volume, very powerful. And over here, you can see that water is heavier than air. Um, Over here, specific weight over here. Very interesting that they use this over here because we'll use this for other stuff too. So be careful what they mean by it in the particular questions. Specific gravity is kind of used for statics, fluid statics, and then left behind. Ideal gas law is idealization, not truth. We have a universal gas constant that gives you this format. And the viscosity over here. We have a viscosity over here, which is clear. We have some assumptions. You can read them all, but basically saying that even if these assumptions are not met, we'll still use them because you know why? Because ideal gas law is just that goaded. Basically, sometimes if you use it still, it'll make a 10% error. But using it is pretty good. Anyways, with that said, we'll move on. Over here, viscosity is a property that distinguishes between two flows with similar densities, as you can see over here. We have a free body diagram over here. I know it's a little difficult to understand because we haven't got into Navier-Stokes, but this is mostly here to show a few things and this over here, basically. This relationship over here is saying that with the stress force, you kind of get the force over here that's needed for this to drag with a constant U. Um, Over here, we won't talk too much until later on because there's a specific way to look at it with Navier-Stokes that we will do later on. Actually, right now, sooner or later than you think. But hmm. Response to fluid shear stress acts to move fluid in contact with the plate y equal h to the right with constant speed u. The plate of fluid in contact with it moves at the same speed. We should probably change that. There's no slip. These are just boundary conditions, and you'll figure out later on why I keep on emphasizing these stuff. But for now, there is the know the plate velocity, knows the boundary condition over here. There is the fluid velocity because there's no slip, fixed plate. For simplicity problem for linear functions, this is kind of the relation you get, although we are not deriving it yet, so you have to just assume it for now. Why are we giving you all this? Is because to define certain properties like the dynamic viscosity, we kind of need to know a little bit of this because how we figure this out is to a constant u over here, constant velocity over here. And you can kind of see with the constant velocity, you can kind of get this over here, and then we can kind of get the shear, so we can get tau. So that's the reason we have brought that up. Um, Later on, you'll see a more analytical way of looking at it, but you can say experimentally this was found. And for now, that's kind of how all the mu's. And you can see that as you see, there's a certain temperature I give you because the temperature defines the mu for now. Because if I were to give you some other temperature and other gas temperatures, the interaction actually just changes completely. Not completely, but it changes a little bit. For example, for liquids, generally speaking, unless you're dealing with some weird ones, temperature increase means intermolecular force goes down, and that means the viscosity or goes down too. So the dynamic viscosity goes down. Okay, and it's more noticeable on liquids. For temperature, for a gas, it's less noticeable. As the temperature goes up, molecular velocity goes up, and then dynamic viscosity goes up. But you can see over here, it's kind of linear line, so it's not really much to say. Over here, we have dynamic viscosity, and this one's a more interesting version because a lot of people like it. It's really true. Kinetic velocity is important quality too. Notice that unlike dynamic velocity, it involves the unit of mass because of this. Either way, you get these kind of temperatures, and you can kind of see it flips over here. It used to be that in the viscosity in the dynamic viscosity it used to be up the way around, but now air is more high of a number than water. Interesting. But it's not really a big deal. Kind of makes sense with the bottom density over here. But either way, Reynolds number is what we're trying to make clear over here. This is a kingmaker. This is gonna make you it's going to be everywhere in fluid mechanics, and it's going to be one of the founding non-linear and non-dimensional units that you have to know. So as you can see, for large, this happens because of that, but we're not really caring too much about that right now. We're just showing it off for now because we're doing definitions right now, not really. And here's an example. So for example, the Reynolds number for like a Boeing is obviously going to be large, and we kind of know why. It's not really unknown to us. I mean, just plug it into your Reynolds number, what we said earlier, and you get a big number, obviously. Um, Anyways. Here's the thing, laminar means regular flow, and turbulent is regular disorder motion. Usually this happens with high Reynolds number, by the way. This thing happens. So order flow looks like something like this, right? The turbulent flow has like eddies over here that's created, which makes the computation a little bit hard, and it makes it makes it really hard for people to like simulate and all that. Just going to definitions. So non-Newtonian fluid is also still being researched right now. So over here, this is a shear thinning liquid. So as you can go up with velocity, these goes down, so forth, so forth. And then we have a Bauham plasticity, which means that you start from no shear, you add shear until a certain shear. It does not have. It acts like kind of like it doesn't move. I don't know. Should I say a solid? I don't know if I should say a solid because toothpaste is considered that. It's a little hard to describe, but with the description of it, it might make more sense. For example, toothpaste, mayonnaise, shaving cream, it makes sense. You need a certain amount of push to make it work. While the painting, thin painting, like shampoos, like water trickles down, you can kind of feel it in the bathtub a little bit. For example, for shear thickening, cornstarch, you can think about it, put cornstarch into your base, it thickens up. I don't know how to describe it, but it works. Here's fluid compressibility. So fluid are taken to be incompressible usually. For gas, compressibility is important. Equation of state density is a function of pressure and temperature. So here's the thing. I mean, this is actually just thermodynamics. You know the whole chart and how to figure out the pressure and all that. Over here is a simplification of it, which is the ideal gas. I don't like ideal gas often because it is a very big assumption and makes 10% error in CFD codes, but they still do it. So isothermal means constant temperature. Isentropic means pressure over rho k over K is constant K is CP over CV. We know Pacific heat, air property, universal gas, and so on and so forth. It's their Mach number. Mach number is more commonly labeled as M, which is another label for non-dimensional parameters, where C is the sound and the speed of sound, and V is the velocity of fluid relative. So you can kind of see like subsonic is less, subsonic is equal to, and supersonic is greater than. There's actually hypersonic and transonic. We'll explain that later. Hopefully. For fluid assumption, no density change. Therefore, if the Mach number is less than 0.3, it is assumed no density change. For ideal gas, C equals square root of KRT. Very interesting assumption. For air, assume 343 or 107.4. I forgot it's the kilometers. I didn't write it, but at 1 atm at 20 C. Either way, yeah, surface temperature. Liquid have corrosive intermolecular forces considered water in a flux. So here's some things over here. Generally speaking, yeah, there is something here like near surface water molecules, air molecules, and so on create interbalance of net corrosive properties and other stuff like that. I didn't really do much of that right now because there's an entire way of like proving this thing later on that I probably will have to explain to you later. But for now, I'm just gonna brush a little bit of it. There's also when we're dealing with very small delta volume, there's likely no molecules, but as delta volume increase, so we can say continuum mechanics work a region of high L microscopic part generally change. So basically, what's saying is increase, increase, increase. You hit these, you hit these, you hit this, and so on and so forth. Um, Generally speaking, there's some other stuff over here from different lectures, but you can kind of get what I'm trying to put down. So here's the greatest equation that you need to derive firsthand to get everything to make sense, in my opinion. And here is how you start it. You start with the velocity. You do the chain rule on the velocity. And this is from, if you don't know the math class, it's 20E. Take the class first before you take it. So it's like multivariable calculus or something. You need to know that to even start here. So what this is basically A, right? Force A. But you can see over here, why do we have dma is because dm is needed. There's a change in mass coming into something like something like this, like something like how do you explain it? In a system that has water, you can imagine that there's going to be mass in and mass out. So you need another mass material over here. And generally speaking, we have simplified a little bit, but in reality, even if you say like density is changing, um, it turns out that the Navier-Stokes does work. It's just a harder derivation, which we can do. It's not that it's not impossible, but this is a derivation with using this diagram over here. And you can see over here, the small volume over here, we're assuming that the density is kind of in there. Not much to say too much other than that. Yeah, but this is just a chain rule. I should just said that. Anyway, with pressure, there's a Taylor series over here, and you can see with the Taylor series, you can get something like this Taylor series. And then you plug over here as P1 and P2, and you subtract each other over here to get this form over here, which is in return, there's three directions. So you can imagine one, two, three, three directions, one, two, three, which can be summation as a gradient of such. Now, with that said, we can move on, but I just realized something. Huh. I like this derivation, but if I were to do this again, I would have to probably have done d rho dv over here. I know this one works over here, and then made a much grander thing because you're gonna have to no, sorry, like that. And then I would have to do d rho v plus the v d rho multiplied by this whole thing. I know this works because people have been using it for a long time. So someone must have the galls to derive this this way. So this must be true. If you don't know what I'm doing, I'm using a product rule. So in a way of sense, there must have been some derivations that use this method too, and must have simplified it throughout this way, which is incredible. I think that's the conservative form then. I'd never realized it before, but it probably is. Let me just check things right now. Um, because you would imagine how you derive that. And with the conservative form known, because it's quite logical that you use conservative form, yeah, probably somewhere with conservative they figured it out. And from conservative, I know these are true because I can go back and forth from conservative. Ah, that's how they probably proved it then. Yeah, that makes sense. Yeah. Because they probably proved the conservative version too. Because if you look over here, the density is inside everything. So you would imagine the density being inside over here, showcases everything. And if you don't know how to do it, it's really just adding this to here. I get it. So there's another simplification happening over here. I didn't realize. But if you were to add this over here, I think there's another Taylor series you could have done to showcase the derivative change of the density there further. But in the end of the day, it doesn't matter because the conservative was proven, and I've done this before, as equivalent to saying these stuff. I've proven that before in Dr. Sanchez's like I think office hours. I went to his office hours and he proved that even in the case of dense air compressibility, it does do that. So yes, I'm pretty confident that then this is okay to do. There's probably some other stuff. Then the outer part continuity must have come in to fixate that. Ah, that makes sense. Yeah. Okay. Anyway, sorry. I keep on distracting myself because I found something interesting. Either way, you get this form, which is basically F equal ma derivative. And remember, momentum equals dF dt. This is a definition of momentum. So there's an interlock of momentum and force. Although I will mention that if you think about it, the force is also because you're taking a derivative of losing some information, but that's not for me to judge because you can do an integral of it and then do plus c, and you can do a boundary condition to rectify that, which is what we do often, I think, which makes sense. Either way, I should move on. Okay. Anyway, we're dealing with pressure next. And the pressure, we follow the same. Oh, we already did this. Sorry. Pressure, we got that. So next part is doing index notation. So I need to talk about index notation a little bit. So coordinate change over here. So we have I, J, K, 1, 2, 3. Each of these, that means 1, 2, 3, 1, 2, 3 for I, J, and K. So over here, we have this format over here, Einstein summation. So you sum all those up. Einstein summation again. We have some more examples of matrix multiplication, which we can show that these two are equal. Another way of writing this is these forms. I'm sure you have shown this before in other classes. It's a wonderful way to simplify. Yeah. Either way, we have another thing. So free and dummy index. A repeating index is called a dummy index because it's summed. And free index appears once in every term is a free index, as you can see over here. So anyways, second order free index has two free index and so on and so forth. You get the pattern. So the result of matrix is something like this. And you can kind of see what I mean by here. So J cannot be a free index because you're adding those two up. And over here, there's some partial derivative term you can do over here. This is really to show that a gradient is actually just a derivative with a bunch of technicalities, but it showcases that. And a quantical delta is really powerful over here. You can see a quantical delta. And then there's cross product over here with identity. I'm not going too much on it because what we're going to do is basically use them for proofs and you're never going to touch them again until like 5 chapters later. We'll do more proofs on it. Either way, here's how you do it. Isotropic materials are defined as this in your solid mechanics class actually, but most times they don't really teach it this way. But either way, with that said, you can multiply by d to get this form, which gives you this final kind of showcase. Over here, we're going to just give you this. There's a way to like semi-derive it, but at the end of the day, it's physics. So some of the things are just experimentally found, and experimentally found are these things like this. So which gives you plug into here and get the final shear stress strain. Yeah, beautiful, isn't it? Anyways, with that said, we move on to this format over here. So right-hand side over here, left-hand side of this cube. So we do that, we get this, we minus it with Taylor series. We do dx divided by 2, and from MIT, you see a more beautiful like description. I just stole it from it. So I just stole this diagram from them online. It shows a beautiful showcase of divide by 2, divide by 2, divide by 2, divide by 2, and where everything goes over here with the shear diagram. Anyways, how to get the force from it is just a little bit of chain rule over here, as you can see. Nothing much. This is just math. In the end of the day, if you have taken a multi-differential calculus, you know all these concepts before. And then if you took ODE, we know the idea of adding different forces. So when you add different forces, you get this form. And you can obviously say that you can get rid of these like dV, dV. Sometimes I forget to delete them. But as you can see, more simplifications follow because you have this tau, which is dot product over here. This is a dot that tau over here, if you didn't know, and then dV. Parentheses. Actually, we can get rid of dV now. So if you simplify this, you get this form over here. And this form over here, with that simplification, you can finally get through this whole math mess to get this form over here. This is like the mother lode equation over here. There's many ways to like showcase this form. As you see earlier, you saw that like at least three different forms. And yeah, this is equivalent to saying this because I simplified it a little bit by taking the gradient dot inwards and to get this form. Yeah, and then there's conservation mass. Do the same process over here to get this or this. It doesn't matter. It's the same thing. And there's like multiple ways to showcase it, and then you can prove that each one of those ways are the same, and the proofs are long, and you can do it. Either way, we can now move on to questions like this. So we're doing a static question, which basically means no velocity. So you can get rid of anything with u, v, and w. So it's basically almost the whole equation, leaving the end over here. So I didn't mention this, but last time I don't think I did. There is gravity over here. Um, Gravity is a thing, but this is actually called body force. So this is actually a body force, and I should probably mention that over here and not just assume that you know it. So let me just do body force. Or we could just call it body force. What is a body force? Body force is basically a force acting on the whole object, basically. It's the best way to describe it for now. Um, Anyway, so far so forth, the body force gets added here, and we get statics because of that. So in general, the fluid dynamics simplifies to this format over here. Here's a question. I mean, it's a clear question, but it's basically asking us determine the reading pressure over here. And then you can imagine what we're going to do. We're going to stack up these equations because if I move on to the next chapter, we can actually integrate these things over here. We have this form, but everything else cancels out because you can imagine that only the z direction has any body force, so it must be z. So integral over here, integral over here, we get this form over here afterwards. So this is constant, but you can add up different densities to get this. And if you want, you can use some more classical knowledge where these two are in the other side and you move it over here. But you do all that simplification and you get this number over here. Not really that bad, not really, just there. Anyways, we do the same thing over here. We generalize it to this form. We integrate, we find the PA, and we plug in, get 2.90 kilograms, kilonewtons. Over here is more interesting. Here's the question. Basically, this is moving over here. This is the question you were kind of trying to figure out last time, where there was why is this like linear over here, and it's actually two different fluids over here, so it's a little bit more a little bit harder than what I proposed earlier. But there's a bunch of assumptions. Assume laminar, assume fully developed and one dimensional, assume Newtonian laws of viscosity, assume no condition, assume no gradient in the x direction. As you can see, steady state cancels like a lot of it. And basically with steady state, if you look at this form, you can take a dot product over here and realize that you can simplify into this format over here because you have a dVt density over here. I canceled it out, but I just added back in. But there's no density must be constant. In liquid, we assume most of the time is constant, therefore this must be 2. And remember Einstein notation is v dot gradient dot v equal 0. So we get this form over here. With that being said, in the end, because of that, we can cancel something in the shear to get this version over here. Assume fully developed also means that U has to go in this Y direction because it's one dimension. And also, if you think about the flat plate, where else is the velocity going to go? And it's laminar, so it must somehow follow a flow. It must be clean. Laminar means it must be like follow kind of like a clean pattern and not just chaos everywhere. Kind of. I mean, we'll get a more proper definition later on, but it's one dimensional flow. So you can imagine like a bunch of these more cancel styles. So this one is v equals 0. There's also 2D questions, so W goes like out the window. So you can cancel this if you see, over here, we can cancel um, over here because of U. So you can imagine this stays and this stays. The gradient on x actually is 0 too. And the reason you can think about it is because this is velocity, but there's no acceleration or force that causes some kind of like x kind of difference over here. That is like there's a y direction over here, surely, but there's no difference between this point and this point in the x direction. That's how you justify it, but for now we justify it by that. Over here, as you see, if you don't know later on, you practice instability over here because of how there's a velocity difference. There could be instability in these regions, but we're not talking about that yet. Hopefully not yet. So in that sense, we do some boundary conditions. We're here, right? So with that said, oh yeah, we get these two equations, and this is useless for us. This is our equation we need to integrate it twice. We get to do this form. We have boundary condition. We have 4 of them. Because of how we have 2 different fluids, we have 2 different boundary conditions for each one. You plug it in. You use your ODE knowledge to get these constants here. With those constants, you go over here and kind of use math to figure out tau, because we did claim that we're using Newtonian fluids, right? So we take a derivative of this to get these forms. I didn't even bother to solve for B because B is useless for us because we're getting a derivative over here, and that's a constant. So there's a boundary condition for it, but it doesn't matter. You get the lower fluid over here, and you get the upper fluid, and you make them equal to each other. And we know that this is true, so we get this format over here. And that form, if you simplify, gives you this over here. And that's how you solve it. Now, there's a shortcut over here. I mean, you probably realize most classes teach it this way, which is without Navier-Stokes initially. But the shortcut is basically allowing your assumptions to just follow through because you're saying that it's U uniform. I don't like this because it doesn't explain why, and I like the why. Next, we do a little bit of more statics over here. You can see this one has an L2 sign. Why we get the basics trigonometry? Why do we start over here? Well, because in eventuality, we're going to this format over here, which actually has some changes over here. As you can see, H has a U sign over here. That's incredible, right? And G has a sign over here because not all the G's over here going to, because we're doing a coordinate change. There's also changes in Navier-Stokes where there's another G X involved now. There's a G over here does it. But for case of this thing, we can get this form over here. So you can see we integrated that and we get the pressure. And with that pressure, we get this dF equal dA, which means we can take an integral over here to get this final form. With that said, with this final form, there's a bunch of simplification you can do with centroids and all this. This is actually a well-known question. That's why we have all these different properties we can do with statics and all that stuff to get this form down. And then we can use a moment to get this form down to this kind of format over here. Now, the math is shown. It's just a little bit plug in algebra to get this format. And there's a bunch of things, but I do a bunch of questions on it, but the real important part for me is that for you guys to understand is that all comes from Navier-Stokes. No, nothing escapes Navier-Stokes with all these things, and which was lacking when I was taking the initial introduction class. In my opinion, I like to know why. So, yeah, it's great to know all these questions, but if you don't know exactly where it comes from, it does confuse me. But now I do know it comes from Navier-Stokes, no matter what. And all these questions over here, they're beautiful, but at the end of the day, it all comes from the idea of Navier-Stokes, these equations. And that's basically what my introduction definition wants to get to you guys, fluid definitions. Everything comes from Navier-Stokes. So if you know Navier-Stokes enough, you can derive or figure out any kind of weird stuff. It's what I realized now, but back then I didn't. So that's the one single thing I want to get out of here when I'm doing a introduction definition. Like, remember your conservation and momentum and energy because they are kings. There's nothing more, nothing less than these equations. These equations in fluid mechanics are so hard to solve because so much things and so much you can add to them. We haven't even added all of it. We can add the electromagnetism. We can add a bunch of things to here. We can add a bunch of things to here. I haven't seen anyone add something to here. Actually, I kind of did. There you can add chemical like M dot, right? Yeah, I guess you could add something. There's a way to add something here. I remember now. It's a very convoluted thing, but yeah, yeah. Um, anyways, there's more to this equation, but these are the base. Like these are the base. The energy one we'll cover later, long later, because it takes a long time to get into here. These two are relevantly known, but this one energy takes a long time to slimmer in. Anyway, I'm gonna share this whole thing. I will mention there's a few questions over there, but in reality, it reads more like I mean, it reads more like you just read it and figure it out because I kind of gave you all the steps. Like there's really nothing much to say. Like these questions I did in the end, I just gave you all the steps to showcase it. So there's like, yeah, there. The only one I'll say is interesting, because I use moment here, moment equals zero, because we do a hinge over here with the force to balance everything out. But other than that, you can figure everything out. It's not